We have a simple system. The roots add up to 5, and we know they sit exactly 1 unit apart. If we add these two equations together, the betas cancel out. We get 2 alphas, which perfectly equals 6. So alpha must be 3, and since they add up to 5, beta has to be 2. We found our roots without even touching the quadratic formula. Since we know the distance is 1, we found our roots are exactly 3 and 4. Now look back at our original equation. The constant term at the end, k, is simply the product of those two roots. So we just multiply 3 by 4, and our missing k is exactly 12. The puzzle is complete. No engine in the universe can be 100% efficient, not even in theory. Let's see why by building a perfect Carnot engine. In our problem, this engine is operating between two specific temperatures. The hot source is at 400 Kelvin, and the cold sink is at 300 Kelvin. To find the absolute maximum efficiency possible, we use the Carnot formula. It's simply 1 minus the ratio of the cold temperature to the hot temperature. So, what happens when we plug in our actual numbers? The math gets surprisingly simple. We put our cold 300K on top, and our hot 400K on the bottom. The units and the zeros cancel right out. This leaves us with 1 minus 3/4, which evaluates to exactly 1/4, or 0.25. Multiply by 100 to get a percentage, and we find our efficiency is 25%. So even this perfect engine wastes 75% of its heat, making option A the correct answer. What happens to the invisible force between two charges if we suddenly squeeze them closer together and make one of them stronger? Let's start with our base case. Two identical point charges, both plus q, sitting a distance are apart. Because they have the same sign, they repel each other with a force we'll call F coulombs. Law tells us this force is proportional to the two charges multiplied together, divided by the distance squared. Now, let's shake things up. We double one of the charges to plus 2q. And we push them twice as close, so the distance is now r over 2. How much harder are they pushing away now? Let's plug our new values directly into the exact same formula to find our new force. On top, 2q times q gives us 2q squared. On the bottom, squaring r over 2 gives us r squared over 4. Here's where the magic happens. Dividing by a fraction is the same as multiplying by its reciprocal. That 4 on the bottom flips up to the top and multiplies with the 2. That leaves us with 8 times our original formula. The new force is a massive 8F. So, for this question, the correct answer is C. If you add more obstacles to a path, things should slow down, right? Not in electrical circuits. We have 3 resistors, 2 ohms, 3 ohms, and 6 ohms. They are connected in parallel, which means they are stacked side by side. Electricity arrives at the junction and splits up, flowing through all 3 branches at the same time. Because there are multiple paths, the overall resistance actually drops. To find the exact equivalent resistance, we use the parallel circuit formula. We add up the reciprocals of each individual resistor. Let's plug in our specific numbers. We have 1 over 2, plus 1 over 3, plus 1 over 6. To add these fractions together, we need a common denominator. The number 6 works perfectly here. 1/2 becomes 3/6, and 1/3 becomes 2/6. Now we just add the numerators straight across. 3 plus 2 plus 1 gives us 6. So, our sum is exactly 6 over 6, which simplifies to 1. Here is a common trap. This number is 1 divided by our answer. To get the final total resistance, we must flip the fraction. Flipping 1 over 1 still leaves us with exactly 1 ohm. This matches option A. Notice how the total resistance is smaller than even the smallest individual resistor. What happens to a magnetic field when you move away from a wire? The answer might surprise you. This classic exam question asks exactly that. For a long straight wire carrying current I, what is the magnetic field at distance R proportional to? When current flows, it generates a magnetic field that wraps around the wire in perfect, invisible cylinders. Let's mark a point at a distance R from the wire. To find the exact field strength here, we use Ampere's law. The formula tells us the magnetic field B equals mu naught times the current I, all divided by 2 pi r. Notice what's happening. The top terms are constant. The only thing changing is r, and it sits right there in the denominator without any square or cube. This means the magnetic field drops off linearly with distance. The correct answer is 1 over r, option B. What happens when you blast a wire coil with a changing magnetic field? It generates electricity. We are told this coil has 100 turns of wire. Each turn covers an area of 0.01 square meters, and the magnetic field passing through it is changing at 2 teslas per second. To find the induced voltage, or EMF, we use Faraday's law. It states that the EMF in a single loop equals the rate of change of magnetic flux. Since magnetic flux is just the magnetic field multiplied by the area, and our area is constant, the change in flux is just the area times the change in the magnetic field. But we don't have just one loop of wire, we have 100, so we must multiply that single loop EMF by the total number of turns, n. Now we simply plug in our given values. We have 100 turns, an area of 0.01, and a field changing at 2 teslas per second. The math here is beautifully simple. Multiplying 100 by 0.01 perfectly cancels out to exactly 1. 1 times 2 leaves us with a total induced EMF of 2 volts. Looking at our options, that matches choice B perfectly. Finding where an object is just from its image seems like magic, but with lenses, it's pure geometry. Let's sketch our setup. We have a convex lens, and its focal length is 20 centimeters. The problem states it forms a real image at 60 centimeters. Real images are formed by actual light rays meeting, which happens on the opposite side of the lens. Before any math, we need the golden rule of optics, the sign convention. Think of the lens as the origin of a graph. Since the focal point and the real image are on the right side, both our focal length f and image distance v are positive. Now we bring in the lens formula, the master equation that connects focal length, image distance, and object distance u. Let's plug in our known positive values. 1 over 20 equals 1 over 60 minus 1 over e. To solve for our mystery object distance, we just rearrange. Move 1/u to the left, and 120 to the right. Time for some quick fraction math. Let's get a common denominator of 60. 1/20th is the same as 3/60ths. Simplify that, and we get 1/u equals negative 1 over 30. Flip both sides, and u is negative 30 centimeters. That negative sign just means the object is sitting 30 centimeters to the left of the lens. The physical distance is 30 centimeters, making option C our correct answer. If you blast a metal with light that vibrates twice as fast, the electrons don't just fly off twice as hard. They get a strange quantum bonus. When light hits a metal surface, it acts like a particle called a photon. If it packs enough energy, it knocks an electron loose. Albert Einstein showed that the escaping electron's kinetic energy equals the incoming photon's energy, minus a fixed exit fee called the work function. Think of it like a toll booth. Let's call the initial kinetic energy K1. The photon brings in energy h nu, pays the toll phi, and keeps the change. Now, the question asks what happens if we double the light's frequency. Our new photon packs exactly twice the energy, 2h nu. But here is the crucial secret. The metal's toll booth fee doesn't change just because you're rich. You still only subtract a single phi. Let's compare this to strictly doubling our original kinetic energy. 2 times K1 would mean doubling the photon energy and doubling that toll fee. Because our new electron only paid the toll once, it ends up with more energy than if we just doubled K1. The kinetic energy more than doubles, making B the correct answer. You might think glowing gas emits every color of the rainbow, but hydrogen only gives off a few perfectly precise wavelengths. The Balmer series is the set of electron jumps that land exactly on the second energy level. The very first line of this series is the shortest jump, from level 3 down to level 2. Our job is to find the exact wavelength of the light this jump produces. To decode this, we use the Rydberg formula. It tells us that 1 over the wavelength equals the Rydberg constant, R, times the difference of the inverse squares of our target and starting energy levels. Let's plug in our specific jump. The electron lands on level 2, so our final destination is 2. It started at level 3, so our initial level is 3. Squaring those gives us 1/4 minus 1/9. To subtract these fractions, we find a common denominator of 36. That leaves us with our times 5 over 36. But here's the trick. We don't want 1 over the wavelength, we want the wavelength itself. So, we just flip both sides of our equation upside down. Now we drop in the Rydberg constant provided in the question, 1.097 times 10 to the 7th. Crunching those numbers gives us about 6.56 times 10 to the negative 7th meters. To match our multiple choice options, we convert meters to nanometers by shifting the decimal, giving us 656 nanometers. This is a famous, brilliant red light called the H-alpha line, making option A the correct answer. If you have 11 grams of carbon dioxide, how many molecules are you actually holding? We can figure it out without a microscope. To convert a physical weight into a count of molecules, we use a simple bridge. The number of moles is just the mass we have, divided by the standard molar mass. First, we need that molar mass. Let's look at a single carbon dioxide molecule. The central carbon atom weighs exactly 12 grams per mole. Then we have 2 oxygen atoms attached to it on either side. Each oxygen atom contributes 16 grams per mole. Add those up, 12 for carbon plus 32 for the 2 oxygens, and 1 full mole of carbon dioxide weighs exactly 44 grams. So, why doesn't this match our 11 grams? Because we have less than a full mole. We just divide our 11 grams by that 44 gram standard. 11 over 44 simplifies perfectly to 1/4, or 0.25. Which means our 11 grams is exactly 1/4 of a mole, making option A the correct answer. What is the number of unpaired electrons in an iron 2+ ion? If you just count backward from 26, you'll probably get this wrong. We need to find the unpaired electrons in an iron 2+ ion. First, let's look at a neutral iron atom, which has 26 electrons. To become an iron 2+ ion, it needs to lose 2 electrons. Here's the trap. You might think they leave the 3D shell, but they actually leave the outermost 4s shell first. So we are left with exactly 6 electrons in the 3D subshell. Let's draw the 5 3D orbitals as empty rooms to see how they arrange themselves. Electrons follow Hund's rule. Think of them like passengers on a bus. They all want their own window seat first. So the first 5 electrons spread out into separate orbitals. But we have a 6th electron to place. Since all the empty seats are taken, this last one is forced to pair up in the first orbital. Now, simply count what's left. We have one paired set, and exactly 4 electrons sitting completely by themselves. So, an iron 2+ ion has exactly 4 unpaired electrons. That makes option C our correct answer. You might think heavier atoms are always bigger, but the periodic table plays a trick on us. Let's find the largest atom among these 4. Let's look at the vertical columns, called groups. As you move down from sodium to potassium, the atom gains a whole new shell of electrons. But here is the strange part. As you move right across a row, or period, the atoms actually shrink. Magnesium is heavier than sodium, but it's physically small. Why? Because moving right adds more protons to the nucleus. They act like a stronger magnet, pulling that outer shell of electrons closer in. So, to find the biggest atom, we want the most shells with the weakest squeeze. That means going as far down, and as far left on the table as possible. That puts potassium right in the sweet spot. It has the extra shell, but without the extra squeeze. The correct answer is C. You might think sulfur can only form 2 bonds, like oxygen, but in SF6, it completely breaks the rules to bond with 6 fluorine atoms. We need to find the hybridization of its central sulfur atom. Is it sp3, sp3d, sp3d2, or sp3d3? To figure this out, we start with sulfur's valence electrons. Sitting in group 16, sulfur brings exactly 6 valence electrons to the table. It's surrounded by 6 highly reactive fluorine atoms. Each fluorine shares 1 electron with sulfur to form a single bond. Now we count the electron domains around the central atom. We have 1, 2, 3, 4, 5, 6 bonding pairs. Are there any leftover, unshared electrons on sulfur? Nope. All 6 are busy bonding, so we have 0 lone pairs. That is 6 domains total. To hold 6 electron domains, sulfur needs 6 identical hybrid orbitals. It builds these by mixing its standard atomic orbital. It takes 1 s orbital, all 3 p orbitals, and 2 d orbitals. Add them up. 1s plus 3p plus 2d gives us sp3d2. These 6 sp3d2 orbitals push apart to form a perfect octahedral shape. And that gives us our final answer. The hybridization of the central atom is sp3d2, making option C the correct choice. You might think adding pressure to a gas mixture just makes it hotter, but it actually forces the chemicals to literally change their identity. To solve this, we use Le Chatelier's principle. It tells us that chemical systems are stubborn. If you introduce a stress, like increasing the pressure, the system will fight back to undo it. How does a trapped gas lower its own pressure? By taking up less space. Let's count the molecules on each side. On the left, we have 1 mole of nitrogen and 3 of hydrogen, making 4 moles of gas total. Now look at the products on the right. We only have 2 moles of ammonia gas. So the left side is crowded, while the right side is much more compact. When we increase the pressure, the system wants to relieve that squeezing stress. It naturally shifts toward the side with fewer gas molecules, because fewer molecules create less pressure. Since 2 is less than 4, the reaction shifts to the right, churning out more ammonia. So, the correct answer is B. The equilibrium shifts right. If you've ever panicked seeing decimals and logarithms in a chemistry problem, you're about to learn a trick that makes them trivial. Hydrochloric acid is a strong acid. This means when it hits water, it completely shatters into hydrogen and chloride ions. There are no intact HCl molecules left. Because every molecule breaks apart, the concentration of our acidic hydrogen ions is exactly the same as the starting acid. We can write 0.001 as 10 to the power of negative. Now for the core formula. pH is defined as the negative logarithm, base 10, of the hydrogen ion concentration. Let's plug our concentration into that formula. We get the negative log of 10 to the negative third. Here is the beautiful trick of logarithms. A log base 10 simply asks, what power is 10 raised to? The exponent is negative 3, so the log evaluates to just negative 3. The two negative signs cancel each other out, leaving us with a final pH of exactly 3. That matches option B perfectly. You don't need to memorize complex electrochemistry diagrams to find a battery's voltage. You just need to know how to read a simple line of code. This shorthand is called cell notation. To decode it, just remember the ABC rule. We read from left to right: anode, bridge, and cathode. The problem gives us the standard reduction potentials for both metals. Zinc, our anode, is negative 0.76 volts. Copper, our cathode, is positive 0.34 volts. To find the total standard cell potential, we just need the difference between them. The formula is E cell equals E cathode minus E anode. Let's plug in our numbers. The cathode is positive 0.34 volts, and from that we subtract the anode's negative 0.76 volts. Subtracting a negative is exactly like adding. So, 0.34 plus 0.76 gives us a total potential of positive 1.10 volts. This means our zinc-copper battery produces 1.1 volts. Looking at our choices, the correct answer is C. What if I told you that knowing how long it takes for half a chemical to disappear tells you its exact speed limit? Let's crack this kinetics mystery. Let's picture this. Imagine a beaker of glowing blue reactant. In exactly 20 minutes, boom, only half is left. Another 20 minutes? It halves again. That constant halving time is the signature of a first-order reaction. Because this halving time never changes, there's a beautiful, rigid mathematical link between the half-life and the rate constant, k. For first-order reactions, half-life equals 0.693 divided by k. But here is the trick. The problem gives us the half-life, not the rate constant. So we just swap them. The rate constant k is simply 0.693 divided by the half-life. Let's plug in our numbers. Our half-life is 20 minutes, so we divide 0.693 by 20. To do this math in your head, divide by 2 first to get 0.3465. Then divide by 10. We get 0.03465, which rounds neatly to 0.0347. Watch out for the trap. Some options might bait you with seconds. Since we put minutes into our equation, our rate constant comes out in inverse minutes. So, our final answer is 0.0347 inverse minutes. That matches option A perfectly. The rate constant is locked in, and the mystery is solved. You probably learned that acids release hydrogen ions, but there's a broader definition that doesn't need hydrogen at all. Let's test our options to see which one wants to accept electrons. First, ammonia, NH3. Nitrogen has a lone pair of electrons sitting right on top, ready to be donated. Water and the hydroxide ion are in the same boat. Oxygen is packed with extra lone pairs. Because they have electrons to give away, they act as Lewis bases, not acids. But here is the strange part about boron trifluoride. Boron only has 3 valence electrons, forming 3 bonds with fluorine. That gives it a total of only 6 electrons in its outer shell. Because boron's octet is incomplete, it is desperate to accept a pair of electrons to reach stability. That makes BF3 an electron pair acceptor, and therefore, our Lewis acid. Don't let condensed chemical formulas intimidate you. There's a simple step-by-step way to reveal their true IUPAC names. First, let's expand this condensed formula so we can actually see the bonds. We have a CH group attached to 2 methyls, a CH2, and a CHO. To name it, we start by finding the principal functional group. Here, it's the aldehyde at the end, which gives our name the suffix al. Next, we find the longest carbon chain that includes this aldehyde carbon. It's 4 carbons long, making the parent chain a butanol. We always number the chain starting from the aldehyde carbon as position 1, moving down the line. Now look at what's hanging off the main chain. At carbon 3, we have a stray methyl group. Putting it all together, the substituent goes in front, giving us 3-methylbutanol. That matches option A. Have you ever wondered how molecules decide exactly where to attach during a chemical reaction? Meet propene. It has a double bond between 2 very different carbons. When hydrogen bromide comes along, that double bond is about to break open. The pi electrons reach out and grab the hydrogen atom. But where does the hydrogen go? It has 2 distinct choices. If hydrogen attaches to the end, we get a secondary carbocation. If it goes to the middle, we get a primary carbocation. Here is the secret. Molecules are lazy. The secondary carbocation is surrounded by more electron clouds, making it much more stable. So, the reaction almost exclusively takes this top path. Now, the leftover bromide ion swoops in. It attacks that stable positive charge to finish building the molecule. This gives us our major product, 2-bromopropane. This shortcut is called Markovnikov's rule. The carbon that already has more hydrogens gets the new hydrogen. The rich get richer. Looking at our options, the correct answer is clearly B. The other options are either minor products or traps for completely different reactions. You might think finding the coordination number is just about counting molecules, but it's actually about counting handshakes. We are looking at a complex ion. At its heart is a central metal, cobalt. Surrounding it are 6 ammonia molecules, which we call ligands. The question asks for the coordination number. But here is the trick, it is not just counting the molecules. It is counting the total number of direct bonds those molecules make with the metal. To find that out, we have to look closely at our ligand, ammonia. Ammonia has just one lone pair of electrons to share. Because it only grabs on with one pair of electrons, we call it a monodentate ligand. One ammonia means exactly one bond to the cobalt. So, if we have 6 of these one-handed ammonia molecules swarming our cobalt atom, they will form exactly 6 bonds in total. 6 ligands, multiplied by 1 bond each, means our coordination number is exactly 6. That makes option C the perfect match. If you want to make a precise chemical solution, you can't just guess the measurements. Let's calculate exactly how many grams of sodium hydroxide we need here. The big M stands for molarity. It's just a fancy way of saying how many moles of our chemical are swimming in exactly 1 liter of solution. We want a 0.1 molar solution, but we don't need a whole liter. We only want 250 milliliters. Since molarity is strictly based on liters, our very first step must be converting that volume. 250 milliliters is simply 0.25 liters. Now, let's find out how many moles of NaOH we actually need. By rearranging our formula, we just multiply the molarity by our volume. Plugging in our numbers, 0.1 times 0.250 gives us 0.025 moles. But here is the catch. Scales in the lab don't measure in moles, they measure in grams. We need to convert this. To do that, we need the molar mass of sodium hydroxide. We just add up the atomic weights given to us. Sodium is 23, oxygen is 16, and hydrogen is 1. Adding those together gives us a neat and tidy 40 grams per mole. Finally, we multiply our required moles by this molar mass to get our physical weight. 0.025 moles times 40 grams per mole. That perfectly equals 1.0 gram. Just 1 gram of NaOH powder mixed into water, and our solution is ready. This makes option A the correct answer. You've probably memorized the 4 quantum numbers, but do you know which one actually draws the picture of where the electron lives? Let's check our options. First is the principal quantum number, n. This number tells us the main energy level, which really just dictates how big the electron's cloud is, not its shape. Next is the azimuthal quantum number, L. This one is special. It defines the subshell, which actually dictates the physical shape of the orbital. For instance, an s orbital is a sphere, while a p orbital is a dumbbell. Just to be sure, what about the others? The magnetic quantum number, m_L, just tells us how that shape is oriented in space, like whether the dumbbell points along the x, y, or z axis. And the spin quantum number, m_S, only tells us if the electron itself is spinning up or down. It has absolutely nothing to do with the shape of the orbital. So, the quantum number that gives us those beautiful spherical and dumbbell shapes is the azimuthal quantum number. Option B is exactly what we're looking for. You might think a reaction that produces heat would have a positive energy change, but chemistry says otherwise. Let's look at the enthalpy change for an exothermic reaction. Let's break down the word itself. Exo means outside, and thermic refers to heat. So, an exothermic reaction is simply one that releases heat into its surroundings. Enthalpy, represented by H, is essentially the heat energy of the system. The change in enthalpy, delta H, is calculated as the final energy of the products minus the initial energy of the reactants. Because our exothermic reaction is giving away heat to the outside world, the products are left with less energy than the reactants started with. Let's sketch this on an energy diagram. When we plug this into our formula, we are subtracting a larger initial energy from a smaller final energy. This means our delta H must be a negative value. So, whenever a reaction releases heat, its enthalpy change is negative. Looking back at our choices, the correct answer is B. You're given a molecule's basic building block and its total weight, but how do you find its actual chemical formula? The empirical formula is just the lowest ratio of atoms. Think of it as a single puzzle piece. The actual molecular formula is made of these pieces linked together. To find out how many pieces make up the whole, we first need to weigh one single piece. Let's calculate the empirical mass of CH2O. Carbon is 12, 2 hydrogens add 2, and oxygen is 16. That's 30 grams per mole. So, one basic unit weighs 30. But our real molecule weighs 180. To find our multiplier, n, we just divide the total mass by the mass of one unit. 180 divided by 30 gives us 6. This tells us there are exactly 6 of these CH2O units in the actual molecule. To get the final formula, we just multiply every atom in our base unit by 6. That gives us C6H12O6, which you might recognize as glucose. Looking at our options, this perfectly matches option C. If you drop a halogen into a chemical reaction, one of them will strip electrons faster than any other element on the periodic table. First, what exactly is an oxidizing agent? Simply put, it's a substance that forces another chemical to lose electrons. To do that, the oxidizing agent itself must gain those electrons. Let's line up our suspects in group 17. As we move down the column from fluorine to iodine, the atoms get progressively larger. Because fluorine is so small, its positive nucleus is very close to its surface. This makes it incredibly effective at attracting extra electrons toward itself. When fluorine gas gains these electrons, it forms fluoride ions. This process releases a massive amount of energy, known as hydration enthalpy. This combination of a small atom and high energy release gives fluorine the highest standard reduction potential of any element. It sits at the very top of the electrochemical series. Therefore, oxidizing power decreases as you go down the group. Fluorine is the ultimate electron thief, making option A the correct answer. Most students waste time finding the exact roots here, but there's a mathematical trick to bypass all that work. We're asked to find the sum and product of the roots, alpha and beta, for the equation x squared minus 5x plus 6 equals 0. Now, this specific equation is easy to factor. You might quickly see the roots are 2 and 3, which add to 5 and multiply to 6. But what if the equation was a total nightmare to factor? That's where a mathematician named Vieta comes in. He proved that the sum and product of roots are hiding directly in the coefficients. Let's line up our equation with the standard quadratic form. By matching them up, we can clearly see that A is 1, B is -5, and C is 6. Vieta's rule says the sum of the roots, alpha plus beta, is always -b divided by A. So, the negative of -5 divided by 1 gives us exactly 5. And the product of the roots, alpha times beta, is simply C divided by A. That is 6 divided by 1, which gives us 6. So our sum is 5, and our product is 6. Looking at our options, that matches perfectly with option A. We found the answer without ever calculating the actual roots. Most people just memorize a formula for complex numbers, but let's look at what they actually are. Let's find the modulus of z equals 3 plus 4i. To do that, we just plot it on a map called the complex plane. The real part is 3, so we walk 3 steps right. The imaginary part is 4, so we walk 4 steps up. The modulus is just a fancy word for the straight line distance from the center to our point. Look familiar? We just drew a right triangle. To find this distance, we don't need a confusing new formula. We just use our old friend, the Pythagorean theorem. We square the two sides. 3 squared is 9, and 4 squared is 16. Add them up, and we get the square root of 25. The square root of 25 is exactly 5, so the modulus is 5, making option A the correct answer. What if you had to add up 20 numbers in a row, by hand? Thankfully, there's a shortcut to find the sum of this arithmetic progression. First, let's visualize the sequence. The first term, A, is 2. The common difference, D, is 3, meaning each step goes up by 3. And we need to sum up 20 of these terms, so n is 20. To find the total sum, we use the AP sum formula. It might look a bit chunky, but it's just a machine waiting for our numbers. Let's plug everything in. We replace n with 20, A with 2, and D with 3. Now we just follow the order of operations. Outside, 20 divided by 2 is 10. Inside, 2 times 2 is 4, and 20 minus 1 is 19. Next, we multiply 19 by 3. That gives us 57. Adding inside the brackets, 4 plus 57 is 61. Finally, 10 times 61 is 610. That's our sum, which perfectly matches option A. Multiplying out a power of 6 by hand is a nightmare. Luckily, there's a trick to instantly find the coefficient of x squared in 1 plus x to the power of 6. Instead of expanding the whole thing, we use the binomial theorem. For the special case of 1 plus x to the power of n, the term with x to the power of r has a coefficient of n. Choose r. In our problem, the total power n is 6. And because we're looking for the x squared term, our r is 2. So, our coefficient is simply 6. Choose 2. We calculate this using the combinations formula. 6 factorial divided by 2 factorial times 6 minus 2 factorial. That simplifies to 6 factorial over 2 factorial times 4 factorial. To make the math easy, we can expand 6 factorial just until we hit 4 factorial. Now, the 4 factorials on the top and bottom cancel each other out perfectly. 2 factorial is just 2 times 1, which is 2. We're left with 6 times 5, which is 30, divided by 2. That gives us 15. So the coefficient is 15, which perfectly matches option B. By using the general term, you can pull out any piece of an expansion in seconds. You might think arranging the letters of a 5-letter word always gives you 120 combinations. But that's a trap. If every letter were completely unique, we'd have 5 choices for the first spot, 4 for the next, and so on. That's 5 factorial, or 120 arrangements. But here's the catch. We have 2 L's. If we swap their positions, the word still reads exactly the same. Because we can't tell them apart, we've overcounted. The exact same thing happens with our 2 E's. Swapping them doesn't create a new arrangement either. To fix this, we take our total, 5 factorial, and divide it by the number of ways to arrange the identical letters. That's 2 factorial for the L's, multiplied by 2 factorial for the E's. 5 factorial is 120. 2 factorial is just 2. So we divide 120 by 4, giving us exactly 30 unique ways. Option A is our answer. You might think you need a calculator to find the exact sine of 75 degrees, but you actually don't. The secret is that 75 isn't just a random number. It's actually the exact sum of 2 standard angles we already know, 45 and 30. Because we can split the angle, we can use the sine addition formula. It tells us that the sine of A plus B expands into a mix of sines and cosines. Let's plug our specific angles into this pattern. We set A to 45 degrees and B to 30 degrees. Now we just drop in the standard values from our trig tables. The sine of 45 is root 2 over 2, and the cosine of 30 is root 3 over 2. For the second half of the expression, the cosine of 45 is also root 2 over 2, and the sine of 30 is exactly 1/2. Multiplying these fractions together, the first part gives us root 6 over 4. The second part gives us root 2 over 4. Since they share a common denominator, we simply add the numerators together. The exact value of sine 75 is root 6 plus root 2, all divided by 4. Looking back at our original choices, this matches option A perfectly. A tough-looking angle, easily solved by breaking it into familiar pieces. You don't need a ruler to measure distances on a graph. Let's calculate the exact distance between the points 1, 2, and 4, 6. First, let's picture where these points live. Here is our coordinate plane. We have point A at x equals 1, y equals 2. And point B is up here at x equals 4, y equals 6. We want to find the length of the straight line connecting them. We'll call this unknown distance d. To find this diagonal distance, we can build a right-angled triangle. This turns our coordinate problem into a simple geometry puzzle. The horizontal leg is the difference between the x-coordinates. It goes from 1 to 4, so its length is 4 minus 1, which is exactly 3. The vertical leg is the difference between the y-coordinates. It goes from 2 up to 6, so its length is 6 minus 2, which gives us 4. Now, we just use the Pythagorean theorem. The distance squared equals the horizontal leg squared plus the vertical leg squared. 3 squared is 9, and 4 squared is 16. Adding them together gives us 25. So, d squared equals 25. Taking the square root, we find the distance is exactly 5. Looking at our options, the correct answer is C. Finding the equation of a circle is surprisingly simple, especially when it sits perfectly in the middle of a graph. We are asked to find the equation for a circle that has its center right at the origin, 0, 0, and a radius of exactly 5. Let's sketch this out. Here is our coordinate plane. Our circle is centered perfectly at the origin, and its radius, the distance from the center to the edge, is 5. For any random point x, y on this circle, we can draw a right triangle. Thanks to the Pythagorean theorem, the horizontal distance squared plus the vertical distance squared equals the radius squared. This gives us the standard equation for a circle centered at the origin. X squared plus y squared equals r squared. Since our radius is 5, we just plug that in. 5 squared is 25. So, our final equation is x squared plus y squared equals 25. Looking at our options, that perfectly matches option B. Ever wonder how to measure exactly how squished an oval is? That is what eccentricity does. And it is exactly what this question asks us to find. We start with our ellipse equation. It is already in the perfect standard form. X squared over a squared plus y squared over b squared equals 1. By matching them up, we can see our denominators. The larger one, 25, is our a squared. The smaller one, 9, is our b squared. This means our ellipse stretches 5 units left and right from the center, and 3 units up and down. It looks like a slightly flattened circle. To find its eccentricity, we use a special formula. Eccentricity, or E, equals the square root of 1 minus b squared over a squared. Let's plug in our numbers. We just drop in the 9 for b squared, and the 25 for a squared. Now, we just do the math inside the root. Think of the number 1 as 25 over 25. Subtracting 9 leaves us with 16 over 25. Finally, we take the square root of the top and the bottom. The square root of 16 is 4, and the square root of 25 is 5. So, our eccentricity is 4/5. Looking at our test options, that matches perfectly with choice B. You might think dividing by 0 always breaks math, but this famous calculus limit has a surprisingly clean answer. If we just plug 0 straight in, we get sine of 0 divided by 0. Since sine of 0 is 0, we end up with 0 over 0. This is what we call an indeterminate form. Because it's indeterminate, we can't just stop there. We need to see how the top and bottom behave visually as x gets really, really small. Look at the graph of y equals x and y equals sine x. Right near the origin, the curvy sine wave perfectly hugs the straight line. Because they are virtually identical when x is tiny, dividing one by the other should give us exactly 1. But let's prove it algebraically using L'Hopital's rule. L'Hopital's rule says if we have a 0 over 0 limit, we can just take the derivative of the top and divide it by the derivative of the bottom. The derivative of sine x is cosine x, and the derivative of x is simply 1. Now, let's try plugging in 0 again. We get cosine of 0 divided by 1, and since cosine of 0 is exactly 1, our limit evaluates to 1. This is one of the most important standard limits in calculus. Looking at our original options, the correct choice is B. Finding the derivative of a polynomial like x cubed plus 2x might look intimidating, but it's actually just 2 simple steps. To find this rate of change, or the derivative, we don't have to tackle the whole equation at once. Thanks to the sum rule, we can split this into 2 separate, bite-sized pieces. Let's look at the first piece. X cubed. We use the power rule here. Just take that exponent, 3, pull it down to the front, and subtract 1 from the power. Now for the second piece. 2x. The x has an invisible exponent of 1. Bring the 1 down, multiply it by 2, and the x vanishes because anything to the power of 0 is 1. Finally, we just combine our 2 solved pieces back together. Our first piece gave us 3x squared, and our second piece gave us 2. Looking at our multiple choice options, we can confidently say the correct answer is A. You just conquered the power rule step by step. If you double a matrix, you don't just double its determinant. Here's a classic exam trick that catches out almost everyone. Let's lay out exactly what we know. We have a 3 by 3 matrix, A, and its determinant is exactly 2. We need to find the determinant of 2 times A. Remember, multiplying a matrix by 2 means doubling every single entry inside its grid. But when you calculate a determinant, you can only factor out numbers one row at a time. Pulling a 2 from the first row gives us one factor of 2 on the outside. We have to do the exact same for the second row, getting another 2. And the third row gives us a third 2. This leads us to the golden rule for scaling determinants. The determinant of a constant, k times an n by n matrix, is k to the power of n times the original determinant. In our specific problem, the scale factor k is 2, and the matrix size n is 3. We were given right at the start that the original determinant of A is 2. Let's substitute that in. 2 cubed is 8. Multiply that by 2, and we get 16. So, doubling a 3 by 3 matrix actually multiplies its determinant by 8. Our final answer is 16, matching option C. If you think multiplying 2 vectors gives you another vector, you're in for a surprise. Let's calculate a dot product. The rule for a dot product is beautifully simple. You just pair up the matching coordinates, multiply them together, and add up the results. Let's line them up visually. First up, the x-coordinates. We take the 1 from vector A and multiply it by the 4 from vector B. But here is where people make a silly mistake. Watch your signs. For the y-coordinates, we have a positive 2 multiplied by a negative 1. Finally, we grab the z-coordinates. That's 3 times 2. We just add this to our chain to complete the setup. Now we just do the basic arithmetic. 1 times 4 is 4. 2 times negative 1 is negative 2. And 3 times 2 gives us 6. 4 minus 2 is 2. Plus 6 gives us exactly 8. Notice that the dot product is a single number, a scalar, not a new vector. Our final answer is 8, which is option B. If you've ever felt like logarithms were just invented to confuse you, you're not alone. Let's decode this one. A logarithm is just an exponent in hiding. The tiny number at the bottom is called the base. Here, our base is 2. The log is asking, what power do I need to raise this base of 2 in order to get x? And the equation hands us the answer on the right, the power is 5. But how do we actually solve for x? We just rewrite the code. We take our base, 2, raise it to the power of 5, and set it equal to x. Now we're back in familiar territory. 2 to the 5th power just means multiplying 2 by itself 5 times. Let's count it out. 2 times 2 is 4, times 2 is 8, times 2 is 16, and times 2 is 32. So, x equals 32. Looking at our options, that perfectly matches option C. The secret code wasn't so scary after all. You might think of amps or volts when you plug in your phone, but neither of those actually measures the raw amount of electricity. Let's look at this classic question. To understand charge, imagine a copper wire. Electricity isn't just invisible magic. It's made of tiny physical particles moving through this wire. We call the flow of these particles current, but the actual total amount of those particles is the charge. Mathematically, total charge equals the current multiplied by the time it flows. If we look at their standard SI units, current is measured in amperes, and time is measured in seconds. So the unit of charge is an ampere second, which physicists named the coulomb. Looking back at our options, ampere is for current, volt is for potential, and ohm is for resistance. The correct unit for electric charge is the coulomb, making B our final answer. If you double the weight of a moving object, you double its energy. But if you double its speed, something crazy happens. To find out how much energy it has, we need the formula for kinetic energy. That energy of motion is equal to 1/2 the mass times the velocity squared. Now, we just plug in our numbers. We drop the 5 kilograms in for the mass, and the 4 meters per second in for our velocity. But here is the crucial detail. Notice that little squared symbol on the velocity? That means speed matters a lot more than weight. 4 squared gives us 16. Half of 16 is 8, and 8 times 5 gives us 40. Because we used standard units, our final energy is measured in joules. So, looking back at our original options, the correct choice is B, 40 joules. Just remember to always square your speed first. They say gravity disappears in space, but that's a myth. If you go up by the Earth's radius, how much is actually left? This classic physics question asks exactly that. What is the acceleration due to gravity at a height equal to the Earth's radius? At the surface, you are a distance r from the center, and gravity is simply g. But climbing to height r means your total distance from the center doubles to 2r. To find the new gravity, we use the standard formula for variation of g with height. It shows how gravity drops off as an inverse square of the distance. Since we are given that the height h is equal to r, let's substitute that right into the denominator. R plus r is 2r. The r in the top and bottom cancel out, leaving us with 1/2 squared. Squaring 1/2 gives 1/4. So the gravity way up there is exactly 1/4 of what it is on the surface. The correct answer is option C. Stretching a wire to double its length doesn't just double its resistance, it quadruples it. Let's see why. First, let's recall the formula for resistance. It depends on the material's resistivity, its length, and its cross-sectional area. Here is the secret. When you pull the wire, you aren't magically adding more metal. The total volume of the wire stays exactly the same. So, if we stretch it until the new length is twice the original, the wire has to get thinner. The area gets cut in half to balance the volume. Now let's plug these new dimensions back into our resistance formula. That dividing by 1/2 in the denominator flips up to multiply the top. 2 times 2 gives us a factor of 4. So the new resistance is 4 times the original. The correct answer is C. You see colors every day, but do you know which one has the longest wavelength? Light travels as a wave. The wavelength is simply the distance from one peak of the wave to the very next peak. If we look at the visible spectrum, different colors have different wavelengths. Let's start at one end with violet light. Violet waves are packed tightly together. This gives violet the shortest wavelength in the visible spectrum, at roughly 400 nanometers. As we move through the rainbowed colors like blue and green, the waves start to stretch out. But when we reach red at the far end of the spectrum, the waves are stretched out the most. Red light waves stretch to about 700 nanometers, making red the color with the longest wavelength. That makes option C our correct answer. If you want to find the exact center of a curved mirror, you don't need a ruler, you just need a single beam of light. Imagine our mirror is just a slice cut out of a giant hollow sphere. The exact center of that imaginary sphere is called the center of curvature. The distance from the mirror's surface to this center point is our radius, r. Now, if you shine parallel light rays at this mirror, its curved shape bounces them perfectly into a single spot. This is the focus. The distance from the mirror to this focusing point is the focal length, which we are told is 10 centimeters. Here is the beautiful trick of spherical mirrors. That focal point always lands exactly halfway between the mirror and its center of curvature. Because it sits perfectly in the middle, the total radius is always exactly twice the focal length. Let's plug in our numbers. We know the focal length, f, is 10 centimeters. So 2 times 10 gives us a radius of 20 centimeters. Looking at our options, that matches perfectly with choice C. The imaginary sphere this mirror belongs to is exactly 20 centimeters in radius. If you connect two identical resistors together, does the total resistance go up or down? It all depends on how you link them. The question asks for the equivalent resistance of two 4-ohm resistors connected in series. Series just means they are linked end to end. Because the electrical current has no alternate route, it must push through the first resistor, and then immediately push through the second one. To find the total or equivalent resistance, we simply add their individual resistances together. The formula is R equivalent equals R1 plus R2. Let's plug in our values. Both of our resistors have a resistance of 4 ohms. Adding them up, 4 plus 4 gives us a total resistance of 8 ohms. The entire circuit acts exactly like a single 8-ohm resistor. Looking at our options, 8 ohms perfectly matches option C, and that is our final answer. If you plug a standard 100-watt bulb into your wall, you can calculate exactly how many electrons are rushing through it. Imagine our light bulb. The box says it operates at 100 watts. That's its power, the total amount of light and heat energy it pumps out every second. We plug it into a standard socket, which provides an electrical push of 200 volts. This voltage is what forces the electrons to move. But here is the mystery. How many electrons are actually flowing to create that 100-watt glow? That flow is our current, which we call I. To find it, we use the golden rule of electrical power. Power equals voltage multiplied by current. So why doesn't this help us immediately? Because we already know the power. We need to isolate the current, I. Let's divide both sides by voltage. Now we just plug in our numbers. The power is 100 watts, and the push from the socket is 200 volts. 100 divided by 200 simplifies perfectly to 1/2, or 0.5 amperes. That's a relatively small, safe flow for a household appliance. Looking back at our exam options, our calculated current matches option A perfectly. We've got our answer. What if I told you that a flying baseball is actually a wave? Let's look at a famous physics question that explains how. In 1924, Louis de Broglie made a radical claim. He proposed that all matter has a wave-like nature, not just light. Let's sketch what that looks like. He connected a particle's physical properties to its wave properties with one famous equation. The wavelength, lambda, equals Planck's constant divided by momentum, p. Since momentum is simply mass times velocity, we can expand the formula. This equation tells us exactly what is required for an object to have a matter wave. Let's check our options. If an object is perfectly stationary, its velocity is 0. Dividing by 0 means the wavelength is undefined. So, stationary bodies are out. What about photons or electrons? While we easily observe the wave nature of tiny electrons in labs, the math doesn't limit itself to them. It works for anything with mass and velocity. Therefore, the de Broglie wavelength applies to absolutely all moving particles, whether it's an electron or a baseball. If it's moving, it's a wave. If half of a substance vanishes every 10 years, how much is left after 30? Let's solve this problem about radioactive half-life. The half-life is 10 years. This means every 10 years, the amount of the radioactive element is cut exactly in half. We want to know what's left after 30 years. To find out, we divide the total time by the half-life. 30 divided by 10 means 3 half-lives will pass. So, the material halves 3 times. We can visualize this, or just multiply 1/2 by itself 3 times. That's 1/2 to the power of 3. 1/2 cubed equals 1/8. So after 30 years, only 1/8 of the original fraction remains. The correct answer is C. You might think all atoms share electrons equally, but some are incredibly greedy. Let's find the most electronegative element here. Electronegativity is simply an atom's ability to pull shared electrons toward itself in a chemical bond. Imagine a microscopic tug-of-war. On the periodic table, this pulling power increases as we move from left to right across a period. That's because the nucleus gains more protons, creating a stronger positive charge. But as we move down a group, electronegativity decreases. The atoms get larger, putting those outer electrons further from the nucleus, so the pull gets weaker. Let's locate our options. Nitrogen, oxygen, and fluorine are sitting right next to each other in the second row, and chlorine is just below fluorine. Following our trend, fluorine is further right than nitrogen and oxygen, making it stronger. And it's higher up than chlorine, so it wins there too. In fact, the famous chemist Linus Pauling assigned fluorine a perfect score of 4.0 on his scale. It is the reigning champion of the periodic table. So, the most electronegative element among our choices is fluorine. Option B is our correct answer. Look at carbon, the element that makes up all known life. We are told its atomic number, Z, is 6, but how many electrons does a neutral carbon atom actually have? That letter Z stands for the atomic number. It tells us exactly how many positively charged protons are packed inside the atom's central nucleus. So, carbon has exactly 6 protons. Now, the question specifies this is a neutral atom. In physics and chemistry, neutral means there is 0 overall electrical charge. The positives and negatives must perfectly balance. To completely cancel out those 6 positive protons, we need exactly 6 negative charges. That means we must have 6 electrons orbiting our carbon nucleus. So, because a neutral atom's electrons must equal its atomic number, we know carbon has 6 electrons. The correct answer is B. Did you know that most of the air you breathe does absolutely nothing to keep the Earth warm? Let's figure out which gas is actually doing the heavy lifting. A greenhouse gas acts like a thermal blanket. When the Earth's surface releases heat as infrared radiation, these gases intercept it. Let's test our options. Nitrogen and oxygen make up most of the air we breathe, but they are simple, symmetrical molecules made of 2 identical atoms. Because they are so rigid, infrared heat passes right through them without being absorbed. The same happens with argon, which is just a single atom. Carbon dioxide is different. It's a slightly wobbly molecule with 3 atoms. When infrared heat hits it, the molecule vibrates and absorbs the energy, trapping the heat. Because it absorbs and traps this infrared radiation, CO2 acts as a major greenhouse gas. So, the correct answer is C. You might think a neutral molecule has no electrical charges at all. But inside sulfuric acid, there is a hidden, high-stakes tug-of-war over electrons. Our mission is to find sulfur's hidden charge. The golden rule here? The entire molecule is neutral, so all the individual oxidation states must add up to exactly 0. Let's unpack this molecule. We have 2 hydrogen atoms, 1 mystery sulfur atom in the center, and 4 oxygen atoms surrounding it. Hydrogen is the lightweight of the periodic table. When bonded to nonmetals, it almost always gives up an electron, giving each hydrogen an oxidation state of +1. Oxygen, on the other hand, is an electron hog. It usually grabs 2 electrons, so each oxygen sits at an oxidation state of -2. Now we can set up our math. 2 hydrogens at +1 each, plus our unknown sulfur, plus 4 oxygens at -2 each, all equals 0. Let's do the arithmetic. 2 times 1 is 2. 4 times -2 is -8. So we have 2 plus s minus 8 equals 0. Combine the numbers. 2 minus 8 gives us -6. Move that to the other side, and we find that sulfur sits at a mass of +6. Sulfur is effectively missing 6 electrons in this tug of war. Looking at our options, that perfectly matches option C. +6 is our final answer. You've probably seen metals fizz and dissolve in acid, but the gas they release is actually highly explosive. Let's solve this question to find out what it is. When a reactive metal meets a dilute acid, a single displacement reaction happens. The metal essentially kicks out the nonmetal part of the acid to form a salt. Let's picture a real example. Imagine dropping a chunk of zinc into a beaker of dilute hydrochloric acid. The zinc bonds with the chlorine, creating zinc chloride in the solution. But what happens to the leftover hydrogen from the acid? It pairs up and escapes as hydrogen gas. If you hold a lit match near these bubbles, you'll hear a distinct pop sound. So, the mystery gas evolved in this reaction is always hydrogen. Looking at our options, the correct answer is B. You might think all hydrogen atoms are exactly identical, but some are secretly carrying extra weight. First, what exactly is an isotope? Think of isotopes as siblings in an element's family. They have the exact same number of protons, which makes them the same element, but they have different numbers of neutrons, changing their weight. Let's draw the hydrogen family. The most common sibling is protium. It's just a single proton with 1 electron orbiting it. No neutrons at all. This is standard hydrogen, but if we add 1 neutron to the nucleus, we get a heavier sibling. This is called deuterium, or heavy hydrogen. It still has 1 proton, so it's still hydrogen, but it weighs twice as much. Add a second neutron, and you get tritium. It's even heavier, and actually radioactive. So, hydrogen's 3 famous isotopes are protium, deuterium, and tritium. Looking closely at our options, helium and lithium are entirely different elements with entirely different proton counts. And ozone is just a molecule made of oxygen atoms. That leaves us with deuterium. It is the stable, heavy isotope of hydrogen, making A the correct answer. A double bond isn't just two of the same thing. Let's uncover what's really inside ethene, C2H4. To find the number of sigma bonds, we have to draw its structure. Ethene has 2 carbon atoms right at its core. Because carbon needs 4 bonds to be stable, these 2 atoms share a double bond. But here's the secret. A double bond isn't just 2 identical links. The first connection is a strong sigma bond, while the second is a weaker pi bond. Next, we bring in our 4 hydrogen atoms. Each carbon takes 2, connecting to them with single bonds. Every single bond is a direct, head-on overlap. That means all 4 of these are also sigma bonds. Let's tally them up. We have 1 sigma bond in the center, and 4 more on the outside. That gives us a grand total of 5 sigma bonds. So, our correct answer is C. You might think any molecule with an O in its name is a powerful base. But in reality, one of these is a heavyweight champion, and the rest are total lightweights. To a chemist, base strength is all about commitment. A strong base completely breaks apart in water, donating 100% of its hydroxide ions. Let's look at sodium hydroxide. Sodium is a group 1 metal that desperately wants to be a positive ion. When it hits water, it instantly and completely separates, flooding the solution with O-. Ammonium hydroxide, on the other hand, is indecisive. It sets up a two-way street, constantly recombining. Only a tiny fraction actually releases hydroxide at any given time, making it a weak base. And then we have aluminum and copper hydroxides. These metals are incredibly stubborn. They are mostly insoluble, meaning they just sink to the bottom like rocks, hoarding their hydroxide. Because sodium hydroxide is the only one that fully ionizes and actually delivers those O ions, it easily takes the crown as the strongest base. You might think all sodas in chemistry are the same, but missing just one part of a formula completely changes what it does. Let's identify washing soda. Let's look at option A first. NaHCO3. This is sodium bicarbonate. You probably have it in your kitchen right now. It's everyday baking soda, used to make cakes rise, not for laundry. Now look at option B. Na2CO3.10H2O. The first part is sodium carbonate. But notice that .10H2 attached to the end? That means for every single molecule of sodium carbonate, exactly 10 water molecules are locked inside its crystal structure. This hydrated form is what we call washing soda. Just to be thorough, NaCl is regular table salt, and CaCO3 is chalk or limestone. So, our winning formula for washing soda is option B. Table salt seems totally ordinary, but on an atomic level, it's held together by a violent microscopic trade. To understand how salt works, let's meet the 2 actors: sodium, a highly reactive metal, and chlorine, a toxic green gas. Sodium has a tiny problem. It has exactly 1 extra electron in its outer shell, and it desperately wants to get rid of it. Meanwhile, chlorine is just 1 electron short of a perfect shell. So sodium does the logical thing. It completely hands over its extra electron. Because electrons carry a negative charge, losing one turns sodium into a positive ion. Gaining it turns chlorine into a negative ion. And in physics, opposites attract. This powerful electrostatic hug between a positive and negative ion is called an ionic bond. So, when we look back at our question, the bond formed by this complete transfer of electrons is strictly an ionic bond. You might think 1 mole of a chemical means 1 mole of everything inside it. But that's like saying one bicycle only has 1 wheel. This same logic applies to chemistry. Our question asks, how many moles of oxygen atoms are in exactly 1 mole of sulfuric acid? Let's zoom in on a single molecule of sulfuric acid. The chemical formula is basically a recipe. That little subscript 4 tells us there are exactly 4 oxygen atoms built into every single molecule of the acid. Remember, a mole is just a word for a very large batch, just like a dozen. So, if one molecule has 4 oxygen atoms, If you want to avoid getting scurvy like an 18th century pirate, you need one specific chemical. Let's find out which